Hello and welcome to our next video in this module. So today we're going to look at section 9.3 and the last component of determining whether a reaction is thermodynamically favorable. We're actually going to get directly from this, and that's Gibbs free energy. So Gibbs free energy change is going to be represented with a delta G, and if we have this symbol, don't forget that that is standard. And all that means is that the reactants and products are in their standard state. So solutions are at 1 molar, gases are at 1 atmosphere pressure, and so on. So again, let's stress to use thermodynamically favorable as opposed to spontaneous whenever you are describing a reaction, okay? So a process that is thermodynamically favored is going to be one where delta G is negative, okay, or less than 0 as it says here. It will proceed to equilibrium without any outside help. And yeah, okay, so again, do not use spontaneous, try to use thermodynamically favorable instead. So just like what we did with delta H and delta S, we can determine the standard Gibbs free energy change using the free energy of formation for our reactants and products. So that's what we have here, okay? So we take the products first, we sum that up by multiplying the number of moles in our reaction times the Gibbs free energy of formation of each of those products, and then subtract from that the sum of all the reactants. That will give us our delta G. So again, if this is negative, this is going to be thermodynamically favorable. Okay, so let's take a look at a sample equation. So we have methanol and it is burning, right? So when it combusts, it forms carbon dioxide and water. Okay, so let's use our equation. So we want to figure out what the standard Gibbs free energy change of our reaction is. So we use the values for each of our reactants and products. Okay, so let's plug those in. So first we'll take carbon dioxide. We got 2 moles of that, and its standard Gibbs free energy of formation, which is negative 394. Make sure that you have the negative there, so multiply that together. And add to that the water, which is 4 moles from the coefficient, negative 229 from its value here. So this would be 2 moles, 4 moles. These numbers would be negative 394 kilojoules per mole, negative 229 kilojoules per mole. But I couldn't quite fit that, so I didn't. But just know that those values, those units should be there. Okay, and then subtract from this the reactants. So our methanol, negative 163 kilojoules per mole times 2 moles. And then the oxygen, which is going to be 0. And we put those together. So we've got, oh, I made a mistake here. So this should be negative 1704. This should be negative 326. And that would give us negative 1378. So I do acknowledge that this should be negative and this should be negative according to what we have up here. I'll have to fix that after recording this video. All right, here's another practice problem. Why don't you try what we just did on the last slide with this. Okay, so remember this, you will have to figure out the values for the Gibbs free energy for each of these. All right, so we need to sometimes figure out what the change in Gibbs free energy for a reaction is going to be, and we can do that if we know the temperature of the reaction, if we know the entropy, if we know the enthalpy. Okay, so if we know enthalpy, we know the entropy, we can figure out what the delta G is going to be. Okay, so for example, the freezing of water or the dissolution of sodium nitrate, we can figure that out if we know these. Okay, so here's our equation. We can determine the Gibbs free energy change of a reaction if we know the enthalpy change of that reaction and the entropy change of the reaction, and also the temperature that it is situated at. So we can actually determine if a reaction is going to be thermodynamically favorable, as in if this value right here, the delta G, is negative or not. Okay, so if we know the value of our delta H or the value, and the value of our delta S, we can determine the temperatures at which the reaction will be thermodynamically favorable, where this would be negative. Okay, so in the first row here, if delta H is negative and delta S is positive, well, we get a negative number here. We would then get a negative number here once this is multiplied, because remember, T in Kelvin is always going to be positive, so this would be negative. So that means that this is negative, this is definitely negative, this will absolutely be negative. So delta G, no matter what the temperature is going to be negative. Okay, so at all temperatures, if our enthalpy change is negative, so it's exothermic, and the entropy change is positive, as in the entropy increases, that's going to be a thermodynamically favorable reaction at any temperature. All right, but what if we make some changes? What if this is positive, so it's endothermic, and this is negative, as in the entropy is decreasing? Well, that is never going to be thermodynamically favorable. So at no temperatures will this be thermodynamically favorable. Okay. Now, what about if this is positive, so it's endothermic, and this is positive, as in the entropy increases? Well, if this is positive and this is positive, this number is definitely going to be subtracted from this. So if T is large, then that will help to make this to be more thermodynamically favorable. Because if this is large and this is positive, then we're going to have a large negative number subtracted from this. Okay? So at high temperatures, if we have a positive enthalpy and positive entropy, high temperatures will give us thermodynamic favorability. But what if these are both negative? If we have an exothermic reaction and a decrease in entropy, well, now if this is negative and this is also negative, that means that this is going to be added onto this, because the negative and the negative here will cancel out, and we'll add this. So that means that if this is negative and this is positive, well, if this is a low number, then that would help to ensure that this negative number will be larger than the product here. Okay, that will get added onto here. So that will help to make delta G still be negative. So at low temperatures, if this is negative and this is negative, our reaction will be thermodynamically favorable. Okay, so if you set up the reaction like this, right, delta H, delta S, you can look at the symbols, and if this is less than 0 and this is greater than 0, they'll be facing each other. And if these symbols set up in that way, that means that it'll always be thermodynamically favorable. Right? But if they're facing away from each other, as in this is greater than 0, this is less than 0, okay, positive, negative, that will never be thermodynamically favorable. Now, if they're both facing to the left, meaning that they're both positive, that means that at high temperatures, this will be thermodynamically favorable. Or if they're both facing to the right, meaning that they're negative, at low temperatures, this will be thermodynamically favorable. Okay, so just a couple of tricks there. And now on this slide, I'm basically telling you the same exact thing, that processes will always be thermodynamically favorable if it's exothermic and has an increase in entropy, It will never be thermodynamically favorable if it is endothermic and goes to a lower entropy state. But if they are the same, if they're both positive or both negative, then we have to actually calculate it out. All right, so that being said, take this practice question and try it out. So calculate delta H and delta S, okay, using what we have done so far, okay, delta S. Do the same thing for delta H, right? We learned this during our first thermodynamics unit, right? But this is what we did in the previous section. All right, once you figure out both of these, then you can plug them into this equation. All right, so this is carried out under standard conditions, meaning that that will be at 25 degrees Celsius. So that should help you to plug in for the temperature. All right, figure it out, and the answers are in the notes in this file. And when you have that done, you're done with 9.3. So I will catch you next in 9.4.